UCSD CE 111, Lecture 6, Set 3, Blocking and Non-Blocking Assignments. There is a difference in terms of how we describe timing to the simulator and to the synthesis tool when we design a combinational circuit as opposed to when we design a sequential circuit. If you remember from what we've discussed so far, or what you've seen in terms of the logic design, here in a sequential circuit, which is the realistic case for most of the designs today, we have the combinational circuit that transforms the current state to the next state, but this also uses the memory elements here, and the memory elements are all orchestrated or synchronized using the clock. So the combinational circuit, what happens in real life if you have a combinational circuit, it's kind of simple. Anytime any of your input values changes, that impacts the output values, the output value will change. Assuming there is ideally there is no delay in the logic propagation delay, this just directly translates to the output, and the intermediate values don't store the previous values that they had. This is examples of this circuit we've seen and we discussed last time are in lecture 4 and 5 are like full adder, half adder, multiplexers, decoder, encoder, comparator, etc. Now in sequential circuits, we have this combinational circuit, as I mentioned, that transforms the current state to the next state, but also the next state is anytime you tick the clock, the next state that was from the previous clock is going to be transferred across this memory element and becomes the current state. So this is a memory element, and we've seen examples of memory elements in this lecture. For example, flip-flops, latches, and so on. Now, we should have because System Verilog is a language that we have to describe this in what is happening in hardware and to both simulate and synthesize, we need to have procedural assignments that tell the difference between a combinational circuit, where your input immediately gets translated to the output no matter when it's changing, and when the sequential circuit is happening. So the blocking assignment really represents modeling of a combinational circuit. So here, this blocking assignment is usually equivalent to an equal sign, and it's modeling combinational logic. Of course, the other operands that we've mentioned earlier that model the combinational logic should be in place for this to be valid. The non-blocking assignment is represented with less than equal sign, and this is modeling sequential logic, which means that there is a notion of the clock happening before the assignments take place, and then the assignments are not blocking each other. Let's just go through more technical details to understand what is the basic difference between blocking and non-blocking statements. So the left-hand side variable of a blocking statement gets equal to the right-hand side, but this evaluation and assignment is done in a single step. So the variable on the left-hand side is updated immediately before the next one. So the execution flow is blocked until the current assignment is completed. This is modeling a combinational logic, because if we are basically evaluating the current logic, the next logic that is connected to it is going to be evaluated next. So this is executed sequentially in order in a procedural block. So here, if you had initialized the sum to 2, once we go here, we say sum is a plus b, it's going to update the sum to 15, because that's the value of a and b, and then the product is sum times c. The product is going to get updated to 4 times 15, which is 60. So then the sum of a plus b uses this updated value, and this is using computes this updated value, and this is using that updated value. So there is a precedence in the values in how things are happening. Non-blocking assignment does not have this property. Again, a left-hand side variable is going to get the right-hand side expression with a less than equal sign, but these expressions are evaluated immediately once the clock arrives. So you may have multiple flip-flops. As soon as the the clock comes to these flip-flops, whatever was observed at the output of the input of the flip-flop is going to get translated to the output. The non-blocking assignments can execute in parallel, meaning that if you have multiple flip-flops and you have the values at the beginning of these flip-flops, when the clock comes, they're going to parallel process it to the output. So their order is not important. One thing to remember is that because these flip-flops are not ideal elements in real life, the arrival of the clock to when the Q output becomes available is called the clock to Q propagation delay of flip-flop. This is actually represented by a non-blocking assignment in RTL, even though the RTL code is modeled with zero delay. And this is because the flip-flop skew or the flip-flop delay from the input to its output is something super important, so they made sure that this has an impact. The non-blocking here is used to model the sequential logic. Here is an example. Here, when the initial begin comes means that we are at the first clock cycle. The sum gets a value of A and B, but product is sum times C. So this sum is not the sum that was calculated in the first one. This is sum that was in the memory from the previous cycle. So because this is non-blocking assignment and they execute concurrently. So if we have the previous values, the sum was 2, this is going to use the value 2 and not the value 15 like we saw in the blocking assignment we just saw earlier. Here is another example of swapping variable. If you have non-blocking assignments or a sequential logic, if you have this, at positive edge of the clock, and you use this blocking assignment, this will introduce a race condition. Because the race condition is because we're giving the value of the output, in this case P, the value that we see in the input of the flip-flop. At the same time, we are trying to do this. So unless we use a non-blocking assignment, we will get this race condition with this type of code. So this is something that is not advised to be used because the race condition is not something we want to tolerate in a design. But we want to have designs that are, when we talk about sequential, we have non-blocking assignment. So as the clock comes, if we have less than equal, means that whatever it was in that storage device before the clock comes, I'm going to use it. After that, if it changes, I don't care to what value it has changed. There is basically nothing will happen. So the first example here, that's a race condition. It will not help me swap the values of P and Q, whereas the second condition, the second code here is a valid code. It can actually swap the values. So if the values of P and Q were 5 and 8, at the end of this procedure, P would be getting the value of Q, which is 8, and then Q will be getting the value of P, which was 5. Now let's think how swapping of the variables will happen in blocking assignment or combinational logic. So if you have a combinational logic, we don't have a memory element. So which means if we have two values we want to swap, we can't really do that because, you know, if you put one into the other because there is no memory, you're going to just delete one of the values. In order to do this using blocking assignment, the only way we could do it is to introduce a temp variable. Here, you know, we have this blocking assignment. This will, you know, this will execute p equal q first, and then executes q equal p. So if the initial values were p equals 5 and q equals 8, then p gets the value of the q, which means that the p will be 8 and the q will be 8. So we are erasing really the memory. Whereas if we define this temp values and we store these values in the temp values and then kind of switch them with the temp values, we can swap these two values with blocking assignments. So that to swap values using blocking assignments, we need to have temp variables because they in effect work like a memory that we didn't have before in System Verilog. You know, this is really not recommended. In fact, you know, it is not recommended that you use inside the always add statement like this, the blocking assignments, because, you know, the danger of writing over your variables is more than its benefit. In next set, we will be talking about interdelay and intradelay in the System Verilog.